So welcome everybody. I know this is a tough session because it's right after lunch, and I've been on the other side many a time, and I know how hard it is after you've just had a good meal. Hopefully I won't put you to sleep. Let me introduce myself. My name is Adarsh Pannu, and I'm an STSM at IBM. Basically that means I'm an engineer, and I have been working with Hadoop and Spark for a few years now. My background is actually in data management and now recently in big data management. That's my email address in case any of you want to reach me via email. So this is a two-part set of two presentations. I did a presentation yesterday called Apache Spark, What's in it for your business. I don't know how many of you were in there, but can I just see a show of hands so I can get an idea of any of you? Okay, so not that many people. Yeah, I recognize a few faces. All right. So that was a 20,000 foot view to a 2,000 or maybe a 2 feet view of Spark. Here today, we're going to go underground. And so I want to stay true to the abstract. I actually just added this slide. So really, this is going to be a pretty technical session, and I guess we are all techies here, so that should be okay. But I'm going to show you a bunch of code, and I'm going to actually get into the guts of Spark. If you have not worked with Spark yet, that's okay. You'll still learn, stuff from it. If you haven't been programming in Scala or Java or programming at all, don't worry about it. I'm going to try and generalize it. Ultimately, it's not about the programming language. It's about the concepts anyway. So with that caveat, hopefully you guys won't walk out on me now that I put that slide. Let's see how it goes. So this is really, shallow internals, basically an internal slide. So the question is, why do we care about Spark internals? And obviously, some of us may have an academic interest, but many of us don't really care about it from an academic point of view. We want to write better applications. So my goal is for you to have some concrete takeaways rather than just abstract components as to what Spark does. I want you to be able to go out and, kind of at a high level know when you work with Spark, what should you be really familiar with, and actually, maybe you can use this presentation as a reference even at some point. So I'm actually trying to make it a practical presentation. So I'll start off with a simple application, and I'm going to use that application to run through the Spark stack, okay? And I'm going to cover key concepts in Spark, such as RDDs, which if you're working in Spark, you have to know what an RDD is, right? It's a concept that's thrown around a lot, and I'm going to tell you what an RDD is. It's an enigma out there sometimes, but you would know it's really nothing that complicated. We'll go into the cluster architecture, and then I'll cover the big three portions of Spark. We're going to talk about tasks and scheduling. We'll talk about shuffle, and I don't have time to talk about memory management, unfortunately. I only got an hour. I actually thought we had an hour and a half. But the first two are pretty important. And then all of this builds up for the last bullet, right? You really want to apply things in practice. So let's introduce the simple Spark application that I talk about. And if you were here yesterday, the 5 or so of you, yesterday you recognize this. I like to use this public domain data set for all of my presentations, because it's real data. And what this is it's a data set that comes from the Department of Transportation. And it's a data set that has a record for every flight in the US that was scheduled in the last 25 some years, okay? So it's millions and millions of records. And for each record, we have a bunch of columns or fields, right? Bunch of metadata. Basically, when was the flight scheduled and where was it scheduled from and where was it supposed to land and things of that kind. Let's just drill into, because I'm building this application for you that we're going to run through, so I want you to understand what this data is, and then we'll go through this, okay? It's actually not that complicated. So this is a sample row from this data set. So what this row is describing is that Continental 65, flight number 65, was scheduled in 2004, Feb 5th, 2004. And it was scheduled to fly out of EWR, which is Newark, and go to Los Angeles, and flying a distance of almost 2,500 miles. And then there's a bunch of other stuff in here, like whether it actually took off or not, was it canceled, and other metadata, the flight, the departure time and arrival time and so on. So about 29 columns. Okay, so it's fairly straightforward. I'm going to use this data set to build applications. So I used the same data set yesterday in my presentation, and actually just a quick background in case you missed it. So to me, an analytics platform is really about the questions that you can ask it, okay? And the speed at which, firstly, does it even handle the question that you're asking it? And secondly, how fast does it give you results? And so my entire presentation yesterday was taking this data set and posing a whole bunch of different questions to Spark around data wrangling, around machine learning, around graph processing, around streaming. So if you missed it, try and look at that presentation, because you will see how Spark excels at a whole variety of questions. Today, I'm going to pick another question, which is really not that complicated. I want to know from Spark which airports, right? I have this data which has flights and airports and so on. Which airports handle the most carriers? Okay, so not the most flights, but the most carriers. So for example, Ithaca, my favorite city, has, actually it's a very small airport. I've been there a few times. I think they only have like 3 or 4 airlines. They have like United and American and so on. So the answer for Ithaca would be 4, right, at the end of this query. Not 40 some airlines, but only 4. And Newark has dozens of carriers. I think in the database I saw about 28 or so. So American, United, and so on. So that's my question. And those of you who know SQL would immediately be able to translate it into that query in your mind. So I'm from my database, a data set called flights, I'm grouping by the origin airport, and for each origin I want a distinct number of airlines. Okay? So this is my application. We will go through the guts of Spark with this. But before we do that, like I said yesterday, let's pretend like we are 10-year-olds, and we want to express this problem that I described. We want to first write the application before I go through it. So how would we do it? We have these millions of rows at a time, millions of rows out there, and we start processing them one at a time. So those are just 4 rows I picked out. American flying out of Newark, United flying out of SFO, and American flying out of Newark. Okay? So what would we do as a programmer? We would read the rows, and we would extract the 2 columns you're looking at, right? The airport and the flight code, the airport code and the flight code. So we just simply extract it, and then what do? Then we have to bring all of the rows which represent the same airport together, because only then can we count them. So a 10-year-old would basically do that, right? He would just say, okay, EWR, these are the flights, and SFO, these are the flights. Now at this stage, even though I don't show any duplicates, EWR could actually have a whole massive list of flights, right? Some of them could be American and United and so on. I don't show any duplicates there, but in your mind, just think that they could be like a long list. And so the next step would be for me to discard those duplicates, okay, and end up with the size of the unique set. So I know that Newark, in my example, only had 2, so United and American, and SFO had 1. So that makes total sense. And the next step would be I collate the results and send them to the client. Okay, so a 15-year-old, this is how he's going to do it on paper, right? That's how you do it. There's no other way to do it. Now in Spark, we basically, I've just added the lines of code, Spark code. This is Scala code. So Spark is what I call what you see is what you get, or what you see, what you think is what you write. Okay, there is very little impedance mismatch between your thought processes and the code. So how many lines is that? It's actually 5 lines, right? 5 lines with the collect. And like I said yesterday, do not try this with MapReduce because you're going to run into a few hundred lines of code and probably a couple, actually, I think that is a couple of jobs. So even though I'm going to describe internals real quick, one of the powers of Spark is that it combines the functional style with the iterative style so beautifully that it not only runs your programs faster for you, it makes you faster as a developer. So that part is sometimes lost on people when they talk about speed of Spark. As a developer, it makes me really fast, right? And sometimes the code is like 5-10 times smaller than what you would write in MapReduce. So just file that away in your mind. Okay, so this is the code we've written. It's just stitching various operations together. Let's drill down now. So when you submit this to Spark, this piece of code, what Spark does is pretty much starts making a graph, which is similar to what you wrote, right? This pipeline that you wrote, Spark starts making that. The top level node in this graph or pipeline is a base RDD, and at this stage, an RDD is nothing but a node in your graph, right? It's really the base RDD. It's more than that, and I'm going to get to that on the next slide. But starting from that base RDD, you can actually transform that data into other RDDs. You call these transformed RDDs until you're ready to return the data back to the client. So I've used the word RDD now. I need to drill into it a little more, as I promised. So what's an RDD? It's basically data, or it's basically an operation on data, kind of loosely, right? An RDD is a collection of whatever you want it to be. It could be a collection of rows, it could be a collection of objects, just any kind of collection. Now in Spark, it of course is a key abstraction in Spark because everything is built on top of RDDs. Now there's another nuance to RDDs. It's a collection that can be broken down. It could be partitioned. And it could be actually partitioned across nodes in a cluster. So kind of similar to HDFS, right? Now when you break things down, and store them, then you can immediately run things in parallel. So the good part about RDDs is that they're abstract collections, but you can parallelize them because they're naturally partitioned. And I've already mentioned that RDDs can handle pretty much any data. Now intuitively, you know that there are some RDDs which are actually sitting right on the data because you've created an RDD right on HDFS, or you've created an RDD right on maybe a SQL database or a NoSQL database. Now that RDD is kind of different because it's sitting on materialized data, right? However, other RDDs that you build on top of this guy, the data that flows through them is not quite physical or materialized, isn't it? It's kind of a virtual concept. So Spark doesn't care. To Spark, an RDD is a collection. The collection could be on disk, or the collection could be flowing through it, but it's really just a collection. Okay, so that's, now let me break down so let me just parse that phrase a little more, right? So resilient distributed data sets. It's a data set, of course it's a collection, we know that. It's distributed because it could be partitioned and split across clusters. Now resilient means it can recover from failures, right? So if you lose a partition or more than one partition, then Spark knows how to recreate just that one partition. You don't lose that entire graph, so to say. And that's why they call it resilient. And because of this, and not only that, you can also cache individual partitions of RDDs in memory across the cluster. So there's a lot of benefit that comes from this abstraction, from making it an abstract collection of objects, because now you can cache it, you can recover it, and there's an independence that is built in. And you'll see that as I go into the architecture some more. But because this is an internal presentation, I want to drill down into RDDs just for one more slide, okay? So I've already established that an RDD is a collection of objects. And I've mentioned that it has partitions. It really, to Spark, is 5 things. The first 3 are very important. So it's a set of partitions. If you build an RDD on Hadoop, and Hadoop has splits, then each of those splits can become a partition each. So we know, so no magic there. Of course, RDDs in our application, remember how we built code one on top of the other? We read data and we extract airport and airline code, and then we do group by. So the data is flowing. So you need to know who your parent is. And so RDDs always know what other RDDs they depend on. That's the second aspect in RDDs. It's actually very key to the definition. And thirdly, once you know who your parent is, you have to know how you can compute yourself from the parent. Okay? So if by chance I lose myself, but I have my parent, I can tell my parent, hey, can you give me your data again? I want to compute myself. And this is where the resiliency comes from, right? Because Spark maintains this lineage of, could be very complex code, very complex data pipelines, that if you lose some aspect because your node goes down, or maybe one executor goes down, then Spark talks to the parents all the way up, and it just builds that one little thing. Very neat concept, okay? Just really beautiful the way it was designed. So question is, what happens when you lose your parent? So the parent may have its own parent, but ultimately you go to, let's say you go to HDFS, right? So, I mean, now you will say, you could lose HDFS, then it is a catastrophic failure, right? But I'm not going to go there. So as long as, yes, so as long as you have HDFS, you can always go back to HDFS, right, through many, many steps.
What happened, is this all in memory?
That's a good question. Is this all in memory? No.
Persistence.
That's a little more complicated question. Okay. So yesterday in the presentation, I dispelled several myths about Spark. One of the myths, actually customers that come to me and say, gee, I don't have 20 terabytes of data. I can't use Spark. Okay. And you don't need 20 terabytes of memory if your application doesn't need it. What happens is that when you build a data pipeline, only the records that you need would be in memory. But you could come in and arbitrarily take any particular RDD and say, cache this, and then it comes in memory. So your application has to say, bring it in memory, but if you don't say that, it kind of works like traditional MapReduce, right?
Okay. What happens if that entire node goes down and doesn't come back up? What happens to the result set?
So if the entire node goes down, then the tasks that you've lost, stages and tasks that you've lost, and you will know what these are in a few minutes, those are redone on another node.
What if there's no access to data from the other node?
Well, you are assuming that you have a shared file system like HDFS, and that every node has access to all the data. But of course, there are locality considerations where you may have to bring the data over the network. Yeah. And that kind of piggybacks to your question. RDDs also have preferred locations. So every partition knows where it should really be processed, right? You want to run your logic on your partitions close to the data. You don't want to ship the data across. So that's the 5th part. I skipped part number 4, which is really RDDs also know how the data is partitioned. Is it hash partition? Is it range? Or is it just kind of unpartitioned, so to say, right, without any semantic to it? I just want to make sure I don't, yeah. Okay. So we wrote the code, and I keep promising that I'll run you through the components. But before that, you need a cluster, right? So I'm going to do a little segue. And so you need to have a Spark cluster, which means you need to have a cluster manager running on top. And Spark is actually very adaptive. It can run in many different combinations. This is a really confusing aspect for people who are coming to Spark. because they don't really realize what's running where, okay? So what I want to tell you is there are 4 ways you can run Spark. You can run it locally on your laptop, right, without really having a cluster manager, so to say, a cluster configuration. You can run it on a standalone mode, which is Spark's own little cluster manager. We don't recommend that for production. Or you can run it on Yarn or Mesos. Of course, in a Hadoop environment, Yarn is the only way to go, right, or is the way to go. So we pick Yarn. Now, there are several components that run when you submit a Hadoop, a Spark job. There are things, processes that start up and tasks that run, and I only want to give you a logical picture because where what runs depends on the cluster manager. So at a very logical level, we wrote our application, irrespective of whether it's standalone or Yarn or Mesos, this is what happens. So in Spark, they don't call it an application, they call it a driver for some reason, right? So when I say driver, that really is your application. And so a driver has its main function, and it connects to the cluster manager for scheduling tasks and running them. And the cluster manager, in turn, launches these workers. Spark calls them executors. And workers can run tasks for Spark, and these executors are launched all over your cluster. So you can have many executors for the application we just wrote, transparent to you, but they are running on some or all of the nodes on the cluster manager. And the application talks to the cluster manager for scheduling and stuff, and then it talks directly to the executors when it has to get data back. Logically, this is the picture we have. If you were to drill down, how am I doing for time? Okay, I need to hurry up, I think. An executor is basically a Java virtual machine, okay? And it has the ability to run tasks. So it has these things called slots, where what I have is maybe 6 tasks I can run in this executor. So I'm running 3 right now, and 3 are free, so I can use those, right, for something else. And of course, an executor has it, when an executor starts, it grabs a bunch of memory, and it says, this is my memory, and I'm going to use it for things like in-memory caching that we alluded to. Of course, if your application is not memory intensive and you don't want to cache anything, then you want to tweak those knobs, okay? So there's some memory things, and then there's a whole bunch of internal stuff around shuffle and garbage collection threads, which is generally common for many JVMs. So just one last slide on this cluster picture. So this application that we wrote, if you were running this on a 3-node cluster, okay, then I have node 1, 2, and 3. And what am I doing here? So you see, I have 2 RDDs. I'm sorry, the colors are just a little too much, even for me right now. So we have 2 RDDs, the blue RDD and the purple RDD. And the blue RDD has many partitions, P1 through 6, and the purple RDD has 3 partitions. And basically, each executor has taken ownership of some partition of that RDD, and it's saying, I'm going to crunch this. That's really the picture that you need to file in your mind. That's what's happening at runtime. Of course, the driver or the application, in this case, I'm running it from my laptop, and it's going over the network and connecting and doing all the stuff and then bringing results back. Okay, so that was just a little segue, but let's get back to the code, because I need to really run you through what happens inside. So at a high level, basically it's only 4 things that happen inside. You write the code. Internally, Spark turns that code into a DAG or a graph, and I'll drill into that step in a little more detail. Yeah, Spark actually draws those boxes and those colors and pictures and stuff. I'm kidding, okay. And then the DAG is further split into tasks, stages and tasks. So that's the DAG in the task scheduler. And at the end of it, the tasks are actually run on the cluster. So only 4 stages. And we have done stage 1, okay? So we only have 3 stages to cover. So I'm going to go back to our code again, and these are the 5 lines that I wrote. So just to repeat, I read the data, I extract the airport and the airline code, I group by the airport code, and then for each airport, I am removing all the duplicates for the airlines and counting how many there were, and I'm returning the results. So it's a very functional style of writing the code, and like I've mentioned before, Spark turns this pipeline into a DAG, or a, as we call it, directed acyclic graph. It's directed because it flows in one direction, and then there are no cycles involved, and it's a graph structure. And the nodes in this graph are your RDDs that I mentioned. They are RDDs because they are really a collection of something, right? In this case, collection of rows. And except the topmost RDD is the RDD that's actually sitting on materialized data, but everything else is kind of sitting on virtual collections. But they are RDDs nonetheless. And in fact, so this is how we wrote it. Spark looks at this graph kind of like this. We wrote actions. We said text file and map and group by. Those are actions, functional constructs. Spark builds these objects, and they're actually of class RDD inside Scala. So there's a Hadoop RDD, and then there's a map partitions RDD and a shuffle RDD and so on. So if you're going to be working with Spark, this really would be something that will become you'll become intimately familiar with. There's this mapping. In reality, though, the view that I'm showing you on the left-hand side is a canonical view, right? In reality, the view that we have internally is a more partition-level view, where let's say my data set, flights, only has 4 partitions. Okay, so my first RDD at the top has 4 partitions, and then the next RDD may have its own partitions depending on how your code is written. But that's actually the other more detailed partition-level view. So I hope I haven't lost you already. Okay, so this is just the graph building. Now what does Spark do, right? It takes the graph, I'm showing you the canonical view now with the actions that we wrote, and before it has to run it, it has to break it up into what we call our stages. And each of those stages could be thought of as a data pipeline, and I'll explain to you in the next slide why we call that a pipeline. But stages are really nothing but discrete chunks of processing, and Spark has to basically Spark is saying, hey, I need to do all of this work before I can do this other work, right? So in this case, Spark split it into two stages, 1 and 2, and 1 has to complete before 2. Now, I'm going to tell you why it needs 2 stages. And this is a very important concept. When you're writing Spark, you need to know how many stages, how many partitions, and so on. So let's go back to our example, right? So the same rows, I'm just extracting Newark and American for the first row, and United and SFO, and Newark and American, okay? So you see how until this stage, I can produce the derived record based on the source record. I don't need data from anywhere else. So I can actually pipeline that process. Function 1 applying to the result of function 2, easy, pipelining, no problem. But we have a problem, don't we, right? After this, I need to actually bring together data from nodes that I'm not running on, because EWR, an American and EWR and United could actually have been produced on 2 rows on 2 different machines. So to bring it together, and so Spark naturally has to complete the first process before it can run the second process. So that's why it's 2 stages. I'm going to do a quiz, okay, for those of you who are still with me. I'm going to do a quiz about how many stages you see in some of these jobs as we go along. Yeah. Yeah. Not at this stage. Not at this stage. Yeah. So the question was, does it know about locality at this stage? Well, yes, it knows about locality, but it hasn't used the locality yet, right? But each of the partitions has locality information stuck on it, and that is propagated in the pipeline. Of course, locality changes across the shuffle. You know, my daughter keeps texting me, sorry. Okay. Okay, so we're good, right? We have two stages. The first stage, we read the data and we extract the two columns. Now, so I forgot to mention that the component that does that in Spark is called the DAG scheduler. When you work with Spark, you're going to see on the console, you're going to see lines saying DAG scheduler crapped out. Sometimes it does, okay, and many other messages like that. So there is a next component which has to turn a stage into actual work, into tasks. And you know that, okay, so a task is nothing but data combined with computation. The data is really the rows that are flowing through that RDD, through that partition. That's your data. And the computation is, in this case, there are two computations. Read a record from a split, a Hadoop split, and for each record, get the two columns out. So that's the computation. So Spark bundles that into a task structure. And it then ships the tasks across all the nodes of the cluster. It will ship the tasks to wherever the tasks need to run, and this is where your locality comes in, right? It's going to try and ship the tasks to where the data actually resides. Sometimes that's possible, other times it's not possible because of how loaded the cluster is. Yes, but that information is already carried in the RDDs. Okay, so let me step back. So this picture is a canonical picture. Remember, the actual picture is, you know, I have to go through this. Oh, did I go too far? I think I did. Yeah, so you see this right-hand side picture? So really RDDs have these partitions. Of the 5 things, remember I mentioned that it knows what partitions an RDD makes up. A partition knows where that resides on HDFS. So when the task scheduler comes up, it needs to, and some of this will become clear in the next slide as well, okay? But at this stage, we have not scheduled anything. We are only trying to break up stage into tasks. We haven't actually scheduled the tasks. And this is actually, well, you're building and running. Right after you do all of this, it's going to just run. Yes. So maybe this will make it a little clear. So in effect, the computation, right, is that canonical picture up, but it has, that graph has 4 partitions because my flight data is in 4 partitions. Partition 1, 2, 3, and 4, and these are sitting on HDFS. So I'm going to have 4 pairs, right, of the RDD graph in the partition, one for each partition, and I have 4 tasks. And at this stage, I've internally in the code, I've only created these task objects, right? I've combined these things together, and I haven't actually run them yet. But at that time, I know that task 1 should only be run on these nodes, and task 2 should only run on these nodes when I actually go ahead and schedule them. But I haven't done that yet. That's going to come in the 4th phase. Okay, so far so good. We have 4 tasks. Okay, now let's see how we schedule them. Now we are ready to actually run the job. So it just, as it turns out, in my example, I have 4 partitions across 3 nodes of a cluster. And so the first node has partition 1. The second node, because of replication, has partition, is on nodes 1 and 2. The third is on nodes 2 and 3, and then the last one is only on node 4. Okay, so 2 partitions are just replicated, but 1 and 4 only happen one time. And how many tasks do I have? I have 4, right, on each of those partitions. So let's say my task 1 comes along. Where do you think it should run, right? My task 1 on partition 1 should run on first. That's where it should run. So Spark will talk to Jan or the cluster manager and say, schedule me on 1. And that little RDD graph with the 1 HDFS split is running on node 1. Okay? And then Spark internally says, now I have to run the second task on partition 2. Now, where could that run? It could run on either the first machine or the second machine. Actually, I'm using the word machine and core interchangeably, so pardon me. But really what I mean are machines here. So the second one, if the cluster manager is any good and if Spark is any good, it really should run here, right? After a slight little delay in scheduling, it just runs almost instantaneously. And then you have task 3, which, no surprise, runs there. And at this time, you are running, right? Tasks are now running. Now, fourth one comes along, and the fourth guy has to now wait until the fourth guy finds a free slot on the cluster. Of course, the fourth wants to run on the last machine, no? Because it's, okay, but one got done first. And you would think, gee, let me just schedule 1 on that. But that would not be good because there's no locality. The data is not there. The data is down here. So what Spark does is, just a little segue, I wasn't trying to say this, but Spark has this concept called delay scheduling, where it's going to hold on to that fourth task just a little longer and hope that, you know, maybe a node would come free. And it actually does. So it runs on the third, okay? And yeah, hi. Yeah, in this example, well, in this case, yes. Well, actually, yes, you're right. I'm only showing 1 core per machine. Yes, you're right, absolutely. So I could actually have many tasks. So I think, let me just try to repeat the question. I think this is a very simplified example. In reality, as I showed you, an executor can run many tasks, which can, right? And you can have many executors on the same node. And that might fry our brain right now, but you're right, what you're saying can happen. Absolutely. And that actually does happen in a real world cluster. You could also do that. Yes, you could also do that. Yeah, I'm not going to go there right now just because I want to stick with a simpler example, but you're totally right, yes. Okay, so how are we doing for time? Oh, I need to hurry up because I haven't gone to the actual meat, right? So one thing that you need to realize here is that, you know, this is a suboptimal situation because we took kind of twice the time. We had like fewer cores than partitions. So the last guy is kind of running and nobody else is running, right? The two. So just file that in your mind. Okay, let's see. I have 20 minutes. I need to cover shuffle. Okay, so after this, stage 1 is done, right? Everything was pipelined. And we have our nice little pairs of airline airport code and airline code. And we have already established that now we need to move data, and there is shuffle involved. And shuffle basically has to redistribute your data. Did I skip a slide? I'm sorry, no, I didn't. Actually, I did, yes. So shuffle has to now redistribute data which is output from stage 1 to all of the consumers in stage 2. So it's kind of an all-to-all data movement, right? Also happens in MapReduce. And logically, the way it happens is that, let's say my stage 1, how many partitions did we have? We had 4, right? And let's say that, so 4 producers, I would call it. Let's say my stage 2, I decide that from that point on, I'm only going to use 2 partitions. Okay, and I can see that in Spark that after a shuffle, only use 2 partitions. So then I'm moving data from 4 outputs to 2 inputs. And that distribution happens typically in a hash partition way, but you could control it. You could control it by writing a user-defined partitioner. Now, I would say that this is usually, Spark usually tries to avoid this if it knows that the data is already partitioned in the right way, and then it is going to avoid the shuffle for you. Another thing to realize is shuffle is actually, it can be a very expensive operation because you're moving data across. So you want to, if you can, not shuffle, right? Oftentimes real-world applications need to shuffle, so you can't really do that. But if you can't do that, at least you want to do some kind of partial work in stage one, partial aggregation, before you ship a lot of the data. In our example, we'll see that as well. By the way, this partial aggregation is similar to what Hadoop also does. It's called map-side combine in Hadoop. The reality in shuffle, okay, so I'm going to skip the slide, right? Just because it's a little, just short of time. I think I took a little too much time on the earlier sections. So presume that our shuffle is done. We went from 4 sets of partitions to 2, okay? Now we have to do stage 2. Stage 2 starts off with a group by, right? And so starting with EWR AA, EWR UA, and so on, we kind of need to make the data come together by key. So similar to the bullets I have there, all the flights for EWR need to be combined under EWR. SFO, same thing, and JFK, same thing. Actually, you'll notice at this stage that JFK has 2 deltas, 2 delta flights, because there are many flights of the same carrier, right? So we're going to have duplicates at that stage. So what Spark does in the group by operation here is it reads all the rows that are coming from the shuffle, and it breaks them up into groups because it's group by. And the grouping happens based on the airport code, and it makes, for each group, it concatenates the values that it needs. So really, it's building a key value pair, again, but the value is a composite. It's a collection. It's a list. Now, traditionally, Spark has been able to, okay, so one obvious problem here is if your lists become too big, then you get into memory issues. Memory pressure builds up. There may be GC issues and GC pauses and so on. So what Spark does is, if any one key becomes too long, it can spill that to disk. But I don't believe Spark can split data from one key onto disk. I don't know if that actually happens yet. Which means when you're writing applications, this is something, there are some APIs which do some of the stuff, you need to be aware of it. But okay, so once the group by is done, everything else is business as usual, right? It's kind of just like stage 1 we did. So stage 1, shuffle, stage 2, maybe there's another shuffle, and stage 3, and it depends on how complex your job has to be, but you could have any number of stages. And at the end of it all, the data has to be acted upon. Either it has to be written to disk or sent to the client, or maybe you're even just doing count or some aggregation or sampling of that kind. All of that happens in the last stage. So you see how, except for the last stage, there's shuffle happening between stage boundaries, right? So stages basically are demarcated by shuffles. Now Spark, they've actually, in the last couple of releases, 1.4 and 1.5, the pictures that I'm drawing for you on the slides, if you write Spark code, you can actually see that in the Spark UI. So every driver or every Spark application opens up a web server, and it has a port, and it starts from 4040 and it goes up 41, 42, whichever one is, and it tells you on your application log. So in my case, I was just running it on a local environment. So you see that picture where it shows you 2 stages. This is actually the Spark UI. In fact, I just created it this morning. So you can see the 2 stages, and you can see the RDDs inside the stages. So it's really very helpful. You can figure out. Similarly, when Spark jobs run, the job that we just ran, it'll tell you, what the job was, and how many stages there were, like in summary. So for instance, we ran 2 stages, and both of them succeeded. And actually, how many tasks did we run? It says 8. Is that correct? 8? Yes, that is correct, right? Because I didn't, even though the shuffle example I showed you 4 feeding to 2, when I actually ran it, I ran it as 4 feeding to 4. So it's 4 plus 4, it's 8 tasks, so that adds up. Not only that, the picture that I showed you around execution, right, where 1, 2, 3, 4, Spark, the UI will show you the same thing as well. So these are your friends. These pictures are really your friends, right? You need to know. So in this case, you see how clear it is that 3 tasks were running, and then the 4th one comes along. The third hasn't really, the 4th hasn't started. And in fact, you can see a breakdown of the task was scheduled, there was a little delay. The task object was deserialized, and then it ran in green, and at the end of it there was a yellow, which stands for shuffle. So you want to look at this, you want the green to be fat, right? You want it to be running. You don't want the blue to be really that much, which means that you have really fat tasks, but they run for a very short amount of time, and you don't want that to happen. Okay, so I have 12 minutes for the meat of the presentation. Right, I just built up for this. So how do you now write better Spark applications? I think there's the big 4, and I've kind of covered some of these, right? You have to worry about partitioning, because that has an implication on how you run. Shuffling, when are you shuffling and how much? Memory pressure, right? In the group buys, we might be building these huge lists, and that may be consuming a lot of memory. And lastly, is your code written the right way? Are you using the right API? Okay, these are just the big 4. There are many other things, but at the very least, these are the important takeaways. So I'm going to cover partitioning explicitly because it's the most important, or at least up there. So you don't want too few partitions because you lose concurrency. We had 4 tasks, we had 3 cores, so we kind of lost concurrency there. And of course, if you have fewer partitions, then some of them, you may have data skew, some of them may be bigger than others, or execution skew, some of them may just happen to take longer than others, and you may have straddlers. You don't want that. And of course, if you have more data and more fatter partitions, then you could have increased pressure, memory pressure. Too many partitions, we do see that sometimes. That means your data is so finely divided that your tasks are really small. You're spending a lot more time just doing admin stuff. Okay, so you need a reasonable number of partitions. I won't go into the bullets because I'm kind of short of time. Similarly, I'm going to skip this. I apologize, just because I want to get to the end of the slide. So let's go through this application, which sounds logical, but it has many flaws, and I want to just correct it, right? Knowing what we know now of the Spark architecture. So a 5-step thing. What do you think? So I have these 4 things that I'm talking about that we need to be worried about. So the first obvious thing is, thank you, 10 minutes. So how many stages did we have? We had 2 stages in this, right? And how many partitions in stage 1? We had 4. And how many cores are we working with, or machines? We have 3. So the most obvious thing is, I want to improve concurrency. So let me just add a repartition off the bat. I take my data, I extract the airport code, so I reduce the data to really, instead of the entire 29 columns, I reduce it to only 2 columns, okay? And then I say, I am going to do 16 partitions. And by doing that, I can fully utilize my cluster. I keep forgetting how many cores there were, 3 cores, okay, good. So I can now run multiple waves of tasks, right? 16 divided by 3. So that's the first thing I do. By the way, how many stages do you see now? Any guesses? Yeah, it's actually 3. Yeah, good. It's 3. You guys are on top of it. So that's stage 1, and then this is stage 2, and this is stage 3. And you may wonder, gee, I've added a stage. More stages aren't necessarily bad. Okay, it just depends on what you're doing. This will run faster than the other one. Okay, may run faster. Okay, let's move on. So what? Okay, the answer is 3. If I go into the administrative UI, this is the picture I'll get in the UIs that I showed you, so you can actually see what's going on. Sorry. Okay, so now I can make another change, right? And what I can say is that I'm flowing all of this data through the shuffle, and some of that data is duplicate. I have these I've generated 16 partitions, but then EWRAA and EWRAA, that doesn't have to flow all the way through the map values across the shuffle. Why don't I just prune these duplicates early on? So I can add a distinct, right? Which means you've got to know the Spark API to know that there is a distinct, right? But I do know that, so I added a distinct. What happens to the stages now, right? I'll just give you the answer. It actually adds a stage, okay? Because distinct has to bring, it's an all to all, and so now we did a repartition all to all, and we did a distinct all to all, so it adds another stage. So you start seeing this graph. Okay, is this good? I don't know. I haven't run this particular thing yet, but I know that, I'm now getting a little nervous, right? I'm just like adding some more stages. But as it turns out, Spark actually has a function called, a parameter called num partitions in distinct. Spark can combine those two. Now, how would you know this? You have to know the API. So if you're writing good Spark code, you need to know the API, right? And of course, how many stages now in this? We go back to 3 stages, okay? So instead of 4, we have 3 stages, and we have 16 partitions right off the bat. So this is looking beautiful. But we're not quite there yet. Okay, by the way, this is the graph for the distinct and the num partitions coalesce together. Okay, we're not there yet because now I look at the code that I wrote, and in the map, when I'm extracting my 2 columns from the airport, this is Scala, by the way, but what I'm doing is I'm extracting column 16, which is airport code, and column 8, which is airline code, and I was splitting the same row 2 times, and you don't want to do that. So it's just simple things. It's just going to make the task run longer. So once again, nothing to do with Spark, but just write efficient code. And so I did that, fine. But I still have another problem, and this is probably the biggest problem right now. I've done the distinct, but I'm still flowing a lot of the data through the shuffle to the other side. And then on the other side, I'm actually doing the grouping, and I'm doing the counting. A very common paradigm in Spark is to group and then count right off the bat. And the way that I've written that on the screen is not the right way to implement this paradigm. I want to reduce the data before the shuffle. I want to do a map side reduction. And so if I know the API, then what I could do is right after the distinct, I build my key value pairs in such a way that I can run a reduce by key. And so reduce by key happens to be a function. It's going to do my data reduction. Some of it it's going to do before the shuffle, and the rest of it it's going to do after the shuffle. Okay? So now the question is, I don't really care about this particular application. I'm really more interested in discussing general ideas. Your application may be completely different and may not lend itself to use of distinct and reduce by key, but I suppose you get the idea, right, of these are some of the things that you need to be aware of. So that was the original. Okay, 1, 2, 3, 4, 5 lines. And then this is my new one. And I actually wanted to time these two on my laptop using just 3 years of the data set, 2008, 9, and 8, 7, and 6. And I actually couldn't finish the first one on my laptop. I just ran out of memory. Because even though intuitively maybe some of your colleagues may write the first one. You've got to tell them, boss, you haven't written the right code here, okay? That probably won't run. The second one just ran in seconds. So it had more stages, and because we repartitioned on the fly, but we fixed up our code, and I made a mistake, didn't I? Right? Yeah, I think it's cut and paste. Yeah, sorry about that. Okay. Yeah, yeah, that's the rewritten one. Yeah. Okay. So I apologize. Yeah, I need to fix that slide. But other than that, yeah, it sounds good. Okay, so the last thing I want to mention before I close is, so writing good Spark applications is about knowing how Spark works, number one, okay? And accordingly writing the best code you could for it. But there are some aspects that I haven't covered which are about the data and the configuration of the cluster, right? If your data is partitioned a certain way, maybe it is ill partitioned, like not adequately partitioned, those are kind of outside the code. Okay, so you need to go in and say, maybe I need to partition it properly. Similarly, your cluster, there are aspects where how many nodes am I running with? How many cores are allocated, or how many tasks or slots are allocated to those cores? How much memory does each executor have? And how is that memory split? Because when you run Spark, it tends to grab all of the memory you've given the executor to itself. But in our case, the group by, we are using so much of the memory, not just Spark. So we need to tell Spark, hey, wait a minute, you give me a little more because my application is a little more memory intensive. So it's not just the code that I showed you, it's some of these other aspects, configuration and data partitioning, that also play a big role in actually writing good Spark applications. So yeah, writing a Spark, once again, a simple Spark job is pretty easy, but writing it efficiently just takes some know-how, some expertise. And just like I did yesterday, many of you are probably starting out on your Spark journey. So what I want to show you is I have reference slides. I'm guessing that you can get these off of the Inside web page. So I have spent a lot of time in building out like a pathway for your Spark journey. Okay, so these are like belts. You can start off being a green belt and a blue belt and a red belt and a black belt. And so you can start off with what you need to do in the first few hours to, weeks and months and years, okay? So, so look at this if you are inclined, and yeah. And other than that, let me just one last slide. I do want to mention that these are some of my buddies, especially Matej Zaharia, and so some of the stuff I wrote down here, I've actually been inspired by their presentation, so I want to acknowledge them here. And that's it. Thank you. I can take questions now.
So how would this differ from a normal MapReduce not using Spark?
Yeah, so the question is, how will this differ from normal MapReduce? I had one slide in the presentation yesterday, and if you, I can pull that up for you, okay? There are quite a few differences. Or let me just relate them. Firstly, MapReduce, I think, is like Morse code, right? Like did-da, it's like map and reduce. Spark allows you to create very complex pipelines. In MapReduce, you do map and reduce, and then you have to flow the data to HDFS. And then you write another MapReduce job, and then it flows to HDFS. Spark, and each of those map and reduce tasks in MapReduce are actually individual JVMs. So they're really fat. In Spark, your tasks are actually pipelined, firstly, beautifully pipelined, and they are threads on a JVM, so they come in and go really quickly. The third thing is, so task scheduling is really faster. Spark uses memory and local disk in ways that MapReduce does not. So things like caching, where you can cache RDD partitions, you don't do that in MapReduce. The use of local disk for shuffle, in keeping shuffle files a little longer so they can be used in the DAG pipeline. That's another. There are quite a few more. Spark Shuffle is actually honestly just faster than MapReduce Shuffle. The benchmark I mentioned yesterday, so Spark guys, the original creators, they ran the 100 terabyte sort benchmark, competed with MapReduce, and Spark took, so 100 terabytes, Spark took 1/10 the machines, virtual machines, not even real machines, 1/7 the cores, and ran in 1/3 the time. So honestly, I don't think there's any comparison, right, in terms of just functionality, expressiveness, or speed. Spark is just better. If that doesn't help you, I can see you outside and I can share some other information with you. Yeah. So when yes, it's many things. You're right. It gives you a whole ecosystem, not just a data crunching platform. Yeah. So there's another question. Yeah.
How do you set up the cluster to prevent the user from using Spark and calling out of memory that will affect the resources that they have?
So you can use it. So basically, you're saying how do you kind of create Spark separate from the rest of the stuff in case Spark. You can use the cluster manager to do that. So you could actually, when you run Spark against Yarn, you can just say, this is my application, and you can configure Yarn to only give it a certain number of executors on some machines and nodes.
Is that an administrative function or the developer doing the code?
Oh, it's configuration, it's DevOps, it's administration, yeah. Okay, thanks again, folks. Yep.